Welcome to tutorial 3.4 part 1, Avogadro's number and the mole. This concept of the mole is a pretty essential one for doing kind of chemical calculations from here on out in the course, so we have to be pretty good at it. But I think you'll see by the end of this tutorial that the calculations are pretty straightforward. The concept of a mole throws people a little bit, so we'll spend a few minutes at the beginning trying to get the concept down. But I think you'll see that the actual calculations are straightforward. So there's some stuff here on the website to help you explain things. I put it in a PowerPoint so I could go through it a little bit more easily on this tutorial. So let's look at the PowerPoint instead. All right. All right. So what is this? What is this thing about? So first of all, what are we trying to do with this concept? Why do we need a concept of a mole? And I'll just read at the top here to make it clear. To analyze the transformations that occur between individual atoms or molecules in a chemical reaction, that is to figure out chemical changes, we actually need to know how many atoms or molecules are contained in a measurable quantity in a lab. If you notice that when we did balanced chemical equations, we'd say things like 2 hydrogens would react with 1 oxygen to make 2 waters. These were all number ratios. 2 of these went with 1 of those to make 2 of those. Another reaction might be 3 of these, go with 4 of those to make 7 of something else. All number relationships, but if you think about it, in a lab or in everyday experience, we actually never see atoms to count them. There's no actual evidence that we say, oh look, I have 7 of these or 7 million of these. We never see a number. So the issue is, how do I go from what I can experience, what I can measure in a lab, a mass, to a number? How do I manage that? And here's the problem. Even the smallest measurable mass has an enormous number of atoms. So we have this like a little bit of almost like a technical problem. Let's say, let's measure really, really small masses so that the number is somehow manageable. Well, the mass is too small to be measured. To have measurable amounts at all, we're going to have to deal with very large collections of objects. So to manage these huge numbers, chemists deal with large collections of a known mass, and they give them a name. Say, okay, let's just have some, even if it's very small mass, a huge number of particles in a particular mass, and just refer to those like as a heap. I have 2 heaps, I have 3 heaps, I have 1 pile, I have 2 piles, and the name of those heaps or piles are called moles. It's perhaps an unfortunate name. The name reminds students too much of an animal, so try not to have that association to confuse you. Alright, so first of all, let's get used to this idea of thinking of things in terms of collections of particles. It's not so unfamiliar. For example, someone sells eggs by the dozen. So if you were working in a grocery store and you wanted to have, oh hey, grab me 6 dozen eggs, that's easier to say, let's say to a coworker, hey, can you grab me 6 dozen of eggs from the back room, than to say, hey, go get me 72 eggs. It's just the number 72 is harder to manage. But if they're sitting there packaged in 12 per carton, it's just a lot easier to go ahead and grab 6. The same would be true of a more old-fashioned term like a gross. Imagine someone had packaged things in terms of gross. Said, hey, give me 3 gross. That's a lot easier than whatever 3 times 144 is. Or perhaps an example that you've thought of, like reams of paper are sold 500 sheets in a ream. It's a lot easier to say, hey, I need 5 packages of paper, rather than say I need 2,500 sheets of paper. That's just a cumbersome number to deal with. So the mole in chemistry works the same way. And all these examples are here to give you some confidence that there's nothing kind of fancy or mystical or weird going on with this idea. It's just a big number, just the way, and just think a dozen because that's the one that's most familiar. The way 12 is just a number. Mole is just a number. It just happens to be this big number. So think of this one part that's going to be important. Think of the word dozen and say, does it matter what I'm counting? Is dozen somehow tied to something like an egg? And you'd say, well, no. You can have a dozen of anything. A dozen people, a dozen stars, a dozen cities. The objects that you're counting have nothing to do with the concept of a dozen. And mole works the same way. I can have a dozen atoms, or I can have a mole of atoms. It's just a certain number. I can have a dozen molecules. I can have a mole of molecules. So notice, like in the case of water, imagine you're trying to count water molecules. If you have a mole of water, each individual thing you're counting is the molecule. If you have a mole of hydrogen, each individual thing you're counting are the hydrogen atoms, just like the word dozen. There's a little bit of confusion here, though. I hope it's not bad. I hope you got the idea what I mean now, or what we mean by the idea of a mole, but there's still some lingering senses if you're normal to say, I don't know, I still find like this number's a bit arbitrary. Like why 6.02? If we're going to count things in convenient ways, why not just like have it be like 1 times 10 to the 50? Why would you cook up this kind of strange number? And exactly how do I work with this number? Like how do I actually manage this translation between masses and number of particles in a lab or just in my everyday thinking about chemical quantities? So let's do a little thought experiment to make sense of this. Imagine that I had a scale, a fanciful scale, one that wouldn't really exist, that could actually weigh out atomic mass units, that is individual atoms. If you remember back from a few lessons ago, we know how to find the relative mass of atoms with a mass spectrometer. So we know, for example, that carbon weighs 12 times as much as hydrogen. The amount of mass is really, really, really crazy small. That's why we have to imagine this kind of imaginary scale. But if such a scale could be developed, you'd have these two scales. When there's one atom on the one side, it weighs 1. For hydrogen, on the other side, it would weigh 12. And now do this small little mental thing. What if you doubled the number of hydrogens? How many hydrogens what would be the mass? Well, of course, 2. And if you double the number of carbons, it would weigh at 24. What would be the point of this experiment? I could keep going. I could put 3 on both sides, 5 on both sides, 1,000,000 on both sides. As long as I had the same number of atoms on both sides, this scale always will read 12 times more than that scale. Make sure it makes sense. As long as I have the same number on both sides, this scale reads 12 times as much as that scale. Now let's go to a real example. I go to the lab, and just as a little bit of a thought experiment, a fanciful experiment. Imagine I have the ability to count atoms. Imagine you could see atoms well enough to actually count them. You can't, but let's pretend. Place them on a scale, and on the scale on the right here, these carbons, and just keep adding them and pretend you're counting. 1, 2, 3. You count and you count and you count until this thing reaches 12 grams. It's going to take you literally forever, but just pretend that you could do it. What turns out to be the number that you end up with when the scale reaches 12 grams? 6.02 times 10 to the 23rd. And hopefully a little bit of a light went off there. You say, oh, okay, all right, so I see where that number came from. The relative mass of carbon and hydrogen is 1 to 12. So on a relative scale, not some kind of actual unit, but a relative scale, carbon has 12 units of mass compared to hydrogen. And if I use the gram, which really has nothing to do with atoms per se at all, it's just this unit, then I have a certain number of carbon atoms on a particular scale when the thing reaches 12 grams. So think of this question. How could you place the same number of atoms on the hydrogen on the other scale? That is, how would you actually put hydrogens in here so that you also had 6 times 10 to the 23rd atoms of hydrogen without actually having to count them? And I think if you think about this for a second, say, oh, well, it's just the reverse logic of what you said before. We said before that when we have the same number of atoms on both sides, this scale always reads 12 times as much as that scale. So if I want to go in the reverse, make sure I have the same number on both sides, I'll just keep adding hydrogens on this scale until the thing reads 1 gram. And that gives you the second idea of why this is valuable. Where the number came from should now make sense. It's just a certain number of atoms relative to the gram. And how we can use it then with knowing the relative masses of all the atoms should also be clear. Whatever relative mass we have, put the unit gram after it, and that will always be the mass of a mole's worth or a certain number of that particular particle. Let's summarize that. A mole is defined as the amount of substance that contains the number of carbon atoms in exactly 12 grams of isotopically pure carbon-12. That's more of a technical detail. We're going to imagine it. Someone could somehow count the carbon atoms on a fancy scale until it read 12 grams. Why does the number seem arbitrary? Because it's based on the notion of a gram. The unit gram, its relationship to a certain number of atoms is somewhat arbitrary. So we just end up with a fact. Well, I counted them, you say, and I counted in 12 grams of carbon, 6 times 10 to the 23rd. Why would I use 12 grams as my reference? Because on a relative scale, carbon weighs 12 times as much as hydrogen. So therefore, since we know the relative mass of all atoms, I can just use that relative mass that's in atomic mass units, turn it into grams, and know that I have a collection of moles worth when I have that number of grams. And that special number, that 6.02 times 10 to the 23rd, is actually given a name. It's called Avogadro's number, and we will just refer to it as a mole. All right, so just a quick, just reiterate to make sure we're really clear. Since we know on a relative scale that carbon weighs 12, oxygen 16, hydrogen 1, if I have 12 grams of carbon, 16 of oxygen, and 1 of hydrogen, they all have the same number of particles, and that number is 6.02 times 10 to the 23rd. Okay, a couple of pictures now just to kind of look at a visual of kind of what this looks like. Imagine the thing you're counting are not atoms, but molecules. Here's a molecule of water shown. How much water would you have until you had 6.02 times 10 to the 23rd water molecules? Not atoms, but molecules. You say, well, I think I can figure this out. This oxygen weighs 16 on the relative scale. Each of these hydrogens weigh 1, so this thing weighs on this relative scale 18 atomic mass units. Therefore, 18 grams must be a mole's worth of water. And here's a picture of a glass, how far it would have to be filled up to have a mole of water in it. Same thing here. Someone said I took a balloon, I filled it up with some oxygen. The mass of this thing is 32 grams. How many particles do I have? Well, that's a mole's worth again, because oxygen, the atom, weighs 16 units on the relative scale. When you stick two together, they weigh 32 units as a molecule. So when you have 32 grams of those molecules, you have a mole of molecules. Same logic here for the sodium chloride and for the water. And finally, just some atoms and just some elements so you don't see compounds. A single zinc on a relative scale weighs 65.4 units. Therefore, when you have 65.4 grams, you've got this a mole's worth, that huge collection of 6 times 10 to the 23rd zinc atoms. Same for carbon, magnesium, etc. All these masses refer to the relative masses when used with atomic mass units. With the unit gram, the mass of a mole's worth. All right, so let's go through 3 types of problems now. The 3 problems are: 1, find the molar mass of something. 2, use it to convert from grams to moles, and then also use it to convert from moles to grams. First, the molar mass of something is trivial. It's the same thing we did in section 3.3. So if you remember there, we said, what does a water molecule weigh? And we just broke it down. We said, well, you have 2 hydrogens that weigh 1 apiece, 1 oxygen that weighs 16 apiece, and we added them up. We're doing the same thing here, except we're always counting in terms of moles. That is, think of it as a box full of particles rather than individual. So 18 grams is what the molar mass is of water. That is the mass of 1 mole of water. An ionic compound works the same way. If you have 3 calciums and 2 phosphate groups in calcium phosphate, just say, okay, what would a single unit of this stuff weigh in atomic mass units? Just add up 3 calciums, 2 phosphorus, and 8 oxygens. When expressed in the unit grams, it's the mass of a mole's worth. So the same exact logic as before, nothing new here. And these just add up to 310.3. What we'd like to now do, and we're not you don't actually get quizzed on this in this section 3.4, but the next 2 types of problems you do, and I hope you'll see that they're pretty straightforward. All right, so the first 2 are going to be a conversion from moles. We're trying to go from grams, to moles. When you have a sample given of grams, 36 grams of water in this case, question is, how many moles do you have? So first of all, let's think of it real common sense. Someone says, look, I have 36 grams of water. Can you tell me how many of these collections that you're calling a mole's worth do I have? And you say, well, that's pretty straightforward. There's 18 grams in a mole of water. That's a certain number of particles, so you must have 2 of those moles. And that's exactly right. However, you might find in some problems that it's a little bit harder to deal with if you don't have numbers that are so easily seen in terms of their relationship. So you might want to set up a ratio that looks like this. If a mole of whatever substance you're dealing with has 18 grams of water in this case, how many moles would you have in 36 grams? And then solve for x. When you solve for x, you kind of, you do it like this. You multiply 36 by both sides. And typically this will be something you could write straight away and not bother with the ratio. 36 times how many in 1 mole? This is 18 grams. The units cancel, and you have 2 moles. So this is method 1. Look at a ratio. Method 2 is just write the relationship like a unit conversion straight away, or just kind of half remember. I mean, I frankly just do this kind of because we've done it so much. Whenever you have a mass, I always want to divide by the grams per mole to get the number of moles. That last thing should kind of seem intuitive to you if you actually think about what you're doing. Someone has a sample of water, 36 grams, and they want to do a chemical reaction with it and say, I need to know how many particles I have there. I mean, I got this mass, this kind of pile over here. Exactly how do I count these water molecules? So you actually imagine filling in boxes of with water that have 18 grams per box. Why 18? Because 18 grams is what a mole's worth is. So once you've dumped all the water in here until it weighs 18 grams, you know you have a mole's worth of water here. And obviously, dividing 36 by 18, the number of boxes you can fill, tells you how many boxes you have of material, 2 in this case. This is a little bit of a fanciful example because you have exactly 2 boxes. Typically, you're not going to have a fraction of a box as well. So 2.66, for example, moles would be 2 boxes and another 2/3 of a box filled up. But the idea is important. You've gone from a mass to a number of particles by knowing how many moles you have. Now let's do another example of this type where we have a gram amount given, a mass given. We want to find the number of moles. How many moles of ammonia are there in a 340 gram sample? Again, just don't do anything except think about it for a second. Say, okay, ammonia, this nitrogen weighs 14 on a relative scale, each hydrogen 1. The mass of ammonia is 17 units, therefore a mole's worth weighs 17 grams. Let's divide that into 340, and what do I have? I have 20. That's exactly right. Each collection, a mole's worth weighs 17, so I've got 20 of those, 20 times that number of particles. Setting it up as a ratio, how many moles do I have in 340 when a single mole weighs 17? Or straight away as a unit conversion type problem is when you're solving this ratio, it ends up being 20. Or just remember from last time, you're just going to divide the mass by the molar mass of the molecule. This again is a nice example. You're saying, okay, I've got this pile, larger pile this time of ammonia. I need to know how many particles I have, the number of particles. I'm just going to divide by 17 because I know how many particles there are in 17 grams. There's 6 times 10 to the 23rd, or a mole's worth. So I know the total number of particles by dividing this by 17. And I refer to it as a mole because it's more convenient than saying the actual number. 20 times 6 times 10 to the 23rd is a pain to deal with, like our example earlier about the dozen. No one wants to say, oh, I have 144 eggs. It's easier to say, I have 12 dozen. Okay, the reverse direction now, you want to know how many grams you have when you're given the number of moles. In some sense, even easier. You know how many boxes you've filled up. You've got 6 boxes of water filled up, 6 moles. They weigh 18 apiece, so 6 times 18 is 108. You could do it as a ratio again. I wonder, and notice we've inverted the ratio. I wonder how many grams we have when we have 6 moles, when there's 18 grams in a mole. Multiplying this out gives us this kind of unit conversion way of writing it. 6 moles times 18 grams per mole gives us 108 grams. Or we just remember, when I have the number of moles, I'm going to multiply to get to the number of grams. And this makes sense, and I hope. We have over here a number of particles. We filled up a total of 6 boxes. They have 6 moles. They have 18 grams per box per mole. So 6 times 18 is 108. So we're going in this direction. Yeah, this stuff is filled. The arrow is showing you this is sitting inside here, but the math is going from this side to the other side. One very last one, maybe a little too long-winded a tutorial maybe you don't need this, but let's do one last one. How many grams of ammonia are in 12 moles? Again, we have 12 moles of stuff, 12 boxes of ammonia. They weigh 17 grams apiece as before, so it's just 17 times 12. Here's setting up the ratio, and here's solving it like a unit conversion problems. I think that I like the pictures best. You're saying, okay, I know how many particles I have. I have it at 12 in the unit moles. 12 times 6 times 10 to the 23rd is some number of particles. Can I figure out how much they weigh? Sure. Take 12 and multiply by 17 grams per box. You have 204 grams of stuff over here. All right, that's it. I think I hope this seemed pretty straightforward. I felt like I was talking a little bit fast. I hope it wasn't too fast. But you'll see when we do section 3.5 and 3.6 and 7, having this concept down super clear is really going to make your life a lot easier when you do those sections. So if this felt like I went too slowly through the stuff or talked too fast for the number of examples given, be patient with it. I think it's worth doing. All right, I will see you in class to practice if we need it.